So hold on a second. Actually, just organic past paper questions and so let's come back to this. Organic past paper question, the first one. That's about so this one is about this molecule. You have to find the optically active molecule carbons. So remember, any carbon that belongs to benzene, that's not chiral. It cannot be optically active. That's kind of impossible for it to be optically active. What is optically active? Optically active is when a carbon has 4 different groups attached to it. It's a tetrahedral carbon atom, and it exists in the form of 2 mirror images. I mean, there are 2 molecules that are mirrored versions of each other. They are chiral, just like your 2 hands. They would look the same, but they would obviously have different shapes, and the orientation of the bonds is going to be different. So chiral carbon atom is, a benzene is never chiral. Remember, a benzene carbon atom is sp2 hybridized. An sp2 hybridized carbon atom looks like this. It's involved in pi bonding, so it can never be chiral. It's a trigonal planar carbon atom. We're looking for an sp3 hybridized carbon atom. So always remember, benzene can never be chiral. This carbon atom over here is bonded to 2 H's. So that cannot be chiral. This carbon atom over here is bonded to 2 H's. How did I figure out it's bonded to 2 H's? That it's making 2 bonds. So the other 2 bonds, the skeletal formula does not show you the hydrogen atoms. So you can add in the hydrogen atoms yourself. This one is also bonded to 2 hydrogens. That's not chiral. Is this one chiral? This one over here. Is this chiral? How many H's would this be bonded to?
1.
Yes, it is.
So there's going to be 1 H, right? And all 4 sides are different. Like if you're standing on this one, the left side is different, the right side is different. And I said, try and use the spacebar to unmute yourself. So all 4 sides are different if you're standing on this carbon atom. I said this one is not chiral because it's 2 H's. This one is making a double bond. That's not chiral. This one is not chiral. It's making a double bond. What about so that's 1. That's 1 chiral. What about this one? Is this chiral? How many H's with this one?
Yeah, it is 1.
1.
So all 4 are different, right? On one side you've got this group, and remember you have to look at the entire group. It's 1 group. That's the H. On the top you have this. On the left side you have this entire thing. So you have to look at the entire side. All 4 sides are different. And I think that's about it. This one is 2 H's. This is benzene carbon atom, so that's not chiral. This one is making a double bond. This one has 3 H's. So you got only 2 chiral carbon atoms, and you're supposed to mark them. So on the diagram of whatever the name is, circle all the chiral carbon atoms. So there are 2 of them. These 2. The next part is the decomposition of this thing produces 3 molecules, J, K, and L. The RO group is unreactive. So whatever this group is, basically when he says that it's unreactive, he just means that it's not doing anything. So it's decomposing. So if you look at this molecule, you would notice what you would notice is let me rub all of this off. So what you'll notice is that there is an amide link. Like if you carefully observe this, there's an amide link, which is this one, and there is an ester link as well. So both esters and amides, they decompose, they hydrolyze. If you have the notes over here, let me just go through amides and esters. We did do esters. Now remember about esters, that esters, they're found when a carboxylic acid and an alcohol react together. The OH and H are lost from the carboxylic acid. The H is lost from the alcohol. and they would end up forming an ester. And the reverse is also true, that they would hydrolyze. The bond will break, and it will break down to form the molecules back again. So just a second. Let's just wait for this. As anyways, esters are formed in two ways. You've got acyl chlorides reacting with alcohols, or you have the other one, which is as anyways, the board has hung up. It's back. So you've got so I'll just briefly go through esters very quickly. Now remember, carboxylic acid and alcohols, they react together to form ester in water. So concentrated H2SO4 in reflux is used. It's a condensation reaction. You can break it back by heating it with dilute acid or dilute alkali. The ester will get broken down back in the middle, and the carboxylic acid and the alcohol would be produced back again. One thing that you should remember is the new thing is that so now the new thing is that acyl chlorides also form esters in the same way. There's no difference. There's an alcohol and there's an acyl chloride, and they end up reacting together, and they're going to form an ester in exactly the same way. But anyways, coming back to the question is, these amides and these esters, they can be broken down. So the molecule is going to break down over here, and it's going to break down at this point. And he's asking us to suggest the possible reagents and conditions for this decomposition. And you're being asked to figure out the third molecule. So one of the molecule is drawn already. So you've got this carbon atom, this one over here.
Mm-hmm.
The double bond O turns into a carboxylic acid. So once it breaks down, so the middle part is gone now. So this part over here turns into a carboxylic acid, where the NH side turns back into an amine. There's an H that gets added over here. So the water molecules, they get added back again, and the bond that was present between them, it's going to break. Then this side would turn into, the double bond O side turns into a carboxylic acid, and the single O side turns back into an alcohol. So what I think the only product that was missing was this methanol molecule. That was the only one that was missing, because he drew the other ones. This turned into a carboxylic acid, this side turned into an amine, this other side turned into, so those things were already there. He had already given us this molecule, and he had already given us this other big molecule. The third one that had broken off, that was not given, so we had to write that one. It was a methanol molecule that is going to be produced.
So how is this methanol produced? I mean, how is this ester converted into that methanol?
How does this?
I mean, this is a ketone, right?
No, it's not a ketone. Achha, ma'am, jaldi se na, I'll just quickly go through esterification very quickly, right? Remember first one, carboxylic acid alcohols, they react, water gets removed from the middle, and they end up forming an ester. The double bond O of the carboxylic acid reacts with the oxygen from the alcohol, and they join up. Okay, so that's one. Remember, phenols don't form. I mean, this is important, that phenols are also like alcohols, but they don't form esters with so these ones over here, phenols, they don't form esters with carboxylic acid, so there is no reaction between them. Acyl chlorides do the same, that the double bond O reacts with the oxygen, they end up joining together to form the ester, and HCl is produced in this case. Acyl chlorides also react with phenols as well, and they also form HCl. The H and Cl, they go away. The carbon positive joins with the oxygen lone pairs, and they end up forming an ester link. I said, anyways, that was esters. How are amides produced? Amides are produced in kind of the same way, that you have an acyl chloride, it reacts with an amine, The lone pair on the N and the carbon, which is very positive, they join up. The H and Cl, they get removed. So the middle part, it forms an amide, which is serial bond ON, NH. Now, if you were to break it back, it's going to break down back into, this thing would turn into a carboxylic acid. This carbon atom over here will turn back into a carboxylic acid. So the OH and H will get added back again. So remember, you've got two groups. You've got an ester group, you've got an amide group. Both of them are kind of formed in similar ways. Acyl chloride reacting with amines, acyl chloride reacting with phenols, or acyl chloride reacting with alcohols. Or you can also have carboxylic acid reacting with alcohols. That's going to produce ester. So coming back to the question, what I saw was, okay, when I broke this molecule up, he was saying it's breaking up. So what I realized was that there is an amide link over here. This is an amide bond. Ibrahim, you clear? Is this is an amide bond? Is this clear?
Yes, it is. Thank you.
And this is your ester link. So I realized that if this molecule is if there's decomposition happening, the only place it's going to break down back again is it's going to break down over here, and this is going to break down at this point. Okay? And when it breaks down, the serial bond will turn back into a carboxylic acid. So this is exactly what he did. I mean, this carbon atom over here, it turned back into a carboxylic acid. Ibrahim, is this clear?
I mean, this molecule is being hydrolyzed back to those molecules, right?
He didn't use the word hydrolysis. He instead used the word decomposition. Decomposition is lysis is decomposition, right? It's the decomposition using water, right? That's the literal meaning of the word hydrolysis. So it is decomposition, and it was pretty clear that this was hydrolysis, that the bond was breaking at this point. This N over here would turn back into what? It will turn back into NH2, right? This double bond O on this side will turn back into a carboxylic acid. So this is what is happening. And this O over here will turn into NOH. It will turn into alcohol. Is that clear?
Yes. Yes.
Baki clear? Saim, is this clear? Munia, is this clear?
Yes, sir. Thank you.
Yes.
Okay, now the next part is suggest possible reagents and conditions for this decomposition. Remember that there are two types of hydrolysis. If you want to break the amide back, so if you want to break, so it's written over here. Boiling an amide with dilute acid or dilute alkali, that would break an ester. That would also break a carboxylic acid back again. So all you have to do is suggest possible reagents and conditions. So it's going to be dilute acid
plus heat.
Now, or reflux. Now the thing is, you can also use dilute alkali as well to do this. But there's one problem with alkaline hydrolysis. And that problem is that instead of forming carboxylic acids, the carboxylic acid part would end up like, if I use NaOH, then I'm going to get the same products, but the carboxylic acid would end up reacting with the alkali. So instead, I'm going to get salts of the carboxylic acid, not the carboxylic acid itself. So always remember, whenever you use alkaline hydrolysis, the carboxylic acid would end up reacting with it. In this case, since it wasn't reacting, so I'm not going to use dilute alkali. Okay? Is that clear?
Yes, sir. Thank you.
The next part is this is obviously hydrolysis. Draw the structure of L in the box. We just did that. Aqueous bromine was added dropwise to a solution of J until the bromine was in excess. State what you would observe. So J. This is J. What type of benzene is this? What do you call this? I mean, he's talking about J.
Phenol.
So that is phenol. So if you add Br2 aqueous to it, what will happen is, so where's electrophilic? Just a second. Is it an activated benzene or is it a deactivated benzene?
It is an activated one.
It's an activated one. So phenol, this is the reaction of phenols, right? We discussed that this is electrophilic substitution of phenols. That the lone pairs on OH and NH2 as well, both of them are activated. The lone pairs, they mix up with benzene, and the electron density becomes really high on positions 2, 4, and 6. So what happens is that if a bromine comes in, it's going to be very strongly attracted to the positions 2, 4, and 6, and the reaction will be very fast. You don't need a catalyst, and bromine will get added on all 3 positions, 2, 4, and 6. So if I were to write bromine, where would the bromine get added? This is position number 2. So bromine will get added at this position, and this is position number 4. I mean, if you take OH as the reference, so bromine will get added to this position. I mean, he's already stated that the RO group is unreactive, so we're assuming that the RO group does not exist. So 2. So this one is position number 2. I mean, if this is 1, then this is 2, this is 4. At the 6th position, there's already something attached, so we're not going to put bromine at that position. Okay, so is this clear that it's a highly activated benzene? So that is, but the question is, what would you observe? That's the question. It's not about what will happen. He's not talking about the reaction. So this is what you're going to observe. If you look at this, you're going to get a white precipitate. Phenols with bromine, that's a white precipitate. So 2 things would be observed. One of them is going to be a white precipitate that would form. And the other thing that would be observed is that the red-brown bromine, Br2 decolorizes. Right? Is that clear?
Yes, sir.
And only one of them would have gotten you all the marks. Now the next one is J has the molecular formula C14. This thing, use this formula to write an equation for the reaction of excess aqueous NaOH with 1 mole of J. So the question is NaOH. Remember NaOH. Let's get rid of this. Let's get rid of the bromines as well. So the question is about NaOH. So which group would NaOH react with? You got
With the OH.
So you got a carboxylic acid, right? And
Okay.
this one is also a carboxylic acid. So there's another carboxylic acid. So this will react with NaOH, right? This one will also react with NaOH. Will the phenol react with NaOH? What did we learn about that?
No, phenol doesn't react with.
Now, let's go back to where did we do comparison of hydrolysis? We did the comparison of acids as well. So this one, we did this table that I said that all organic acids are weak acids. Alcohols are like really terrible acids. You've got carboxylic acids, which are relatively stronger acids. So phenols would react with sodium. They would also react with NaOH. They would not react with weak bases like carbonates and ammonia.
Okay.
So phenols will also react with NaOH. So they would also form a salt. So this phenol over here will also react with NaOH. Is that clear?
Oh yeah, thank you.
Okay. Ibrahim, is this clear? Saim, is this clear? Am I clear? Achha, so remember this phenols, remember this table that alcohols will only react with Na, phenols will react with Na as well as NaOH, but not with weak bases. Carboxylic acids would react with everything. They would have all acid-base reactions. So we did do this table, and now in this case, let's go back to this. What was the question? He was saying write an equation using the formula. So I'm going to write the equation over here. What was the formula? Just a second. He gave us C14H19O6N. C14H19. So this thing is C14H19O is 6 and there's one N, right? So what do you think will be the reaction with NaOH? How many NaOH will react with it? One,
Three.
2, and so it's
Three.
going to be 3 NaOH reacting with that, right? So what will be formed? What will be formed is that the
Solid.
OH, all the OHs will react, the H will get displaced, and Na will take its place. Okay, so that's what's going to happen. This H as well, they would all form salts. So that means the molecule is losing 3 H's and it's gaining how many? 3 NAs, 3 Na plus 1 ions, right? So this is what's happening. It's now C14. H, it lost 3 H's, right? So it's H16 now, and it's O6 and N, and it's got a charge of -3, which means there would be 3 Na plus 1 ions that would join up with it. I'll just check. I don't know how to, I mean, if you do crisscross, it's going to be 3 NAs. It's going to have a charge of -3 because -1 over here and -1 over here as well. And with a base, a water molecule is always produced. With NaOH, a water molecule is produced. So is this clear, this thing?
Yes, sir. Thank you.
And I'll quickly check I'm pretty sure the marking scheme also has this. Maybe they they haven't written the charges. They just wrote down the formula, but you'll get an equation. And there would be 3 water molecules just to balance the equation. Is that clear? I'm clear, Ibrar?
Yes.
What's the next? State what you observe when an excess of aqueous bromine is added to a solution of K. What's K? Now he's adding bromine to K. So what should you observe? And I think he did not add any, to K, right? First thing, is this benzene a normal benzene, or is it a benzene with a carbon chain, or is it a phenol, or is it an amine? What is it?
Benzene with a carbon chain.
Okay, so this is a benzene with a carbon chain. So that's basically an arene. Because the OH groups and the NH2 groups are much further away from the benzene, so they're not attached to the benzene itself. So it's an arene. It's a benzene with a carbon chain. So what happens in that case if we go back to electrophilic substitution? Now benzene with a carbon chain is like a normal benzene. Benzene with a carbon chain, the reactions are not going to be, although the carbon chain has an electron donating effect, but the conditions are the same as benzene. The only thing that will happen is that it's just going to be very slightly faster. That's it. The reaction conditions are kind of the same. So if you want to do bromination of benzene, you would need a catalyst. Now, in this case, if you look carefully there, I don't think there's a catalyst. Like if I go back to the question, when an excess of aqueous bromine is added to a solution of K, nothing should happen. There should be no reaction. Why? Since there is no catalyst added, you need a catalyst for this reaction to happen. Is that clear?
Yes, sir.
There is no FeBr3, there's no AlBr3, no catalyst has been added. So always remember that with alkyl chains, the conditions kind of remain the same for nitration and bromination. But when you go to phenols and phenylamine, that's when the benzene ring is very activated. And in that scenario, you don't need a catalyst. Only Br2 aqueous would be sufficient. So moving on, the next one, K can be polymerized. Draw the structure of polymer showing 2 repeat units, the linkage between the monomers. So K can be polymerized. So let's go back. What is K? Now, if you look at K, K has a carboxylic acid group. It's got an amine group. So this is like an amino acid. Let me just discuss polymerization, especially condensation polymerization. This is something that is very similar to O levels. So if you remember O levels proteins, the monomer had a carboxylic acid group on one side, it had an NH2 group on one side. All monomers, they kind of had the same thing. They had a carboxylic acid and an NH2 group on one side. And it was a condensation reaction. The H and OH were lost. They would turn into water. And the NH and the serial bond O would join up. They would form amide linkages, which were also known as peptide linkages. The serial bond O would join up with NH. This serial bond O would join up with NH. It's exactly the same as an amide link getting formed, but there are lots of amides getting formed in this case. So what is going to happen in this case? You've got two carbon atoms written in that CH2, and then this is C6H5. So let's just. So I think that's one side was carboxylic acid, and it had NH2 on the other one. I think it just had NH. Let me just quickly double check. What was K like? Okay, then right next door it's the next door there's a carbon chain and then there's NH2. So there's a carbon chain that's in the middle. So there's a carbon chain in the middle, and then there was NH2. And on top of that, there was another carbon, and then you had benzene. Benzene is C6H5, right? This one will have two H's, this one will have two H's. So this is what the molecule looked like. I mean, I haven't drawn the benzene structure, but this is what the molecule looked like. So he's saying draw two repeat units. I'm going to draw another one. So there's and this won't be CH2, this is just going to be CH. So there's CH in the middle, there's NH2 on the left side, and there is C double bond O and OH on the right side, and the top there is CH2. And then there is C6H5. What will happen is that the OH and the H are going to go. Water would be formed. And in the middle, there's going to be, so in the middle over here, there's going to be an amide link that will form between the two molecules. And you're going to remove the OH from this side and the H from this side just to show that the structure is continuing. So you just had to show two repeat units. The linkage between the monomer units should be fully displayed, which means that you had to show the bonds. So is this clear, this one? Okay. Munia, is this fine, Saim?
Yes, I thank you.
So now the next thing is, the next one is that we've got he's talking about K again. Carbon-13 NMR spectrum of K was recorded. State how many carbon environments are present in K and so on. So that's a question about carbon-13 NMR spectrum. So we're not going to do that right now. Let's see if there's any other organic questions. So there's another question, organic. Let's do that one. So there's this molecule, and it says that the
paper 4 कितने marks होता है?
Huh?
Paper 4 कितने marks होते हैं?
100 marks.
Oh, अच्छा.
काफी बड़ा पेपर होता है उसके अंदर. There's lots of questions. ठीक है, almost 10 questions. 2 hours. So now you've got this molecule saying that it reacts with potassium dichromate 6. So that is obviously oxidation. So what will happen in this oxidation? This is a ketone. Do ketones get oxidized?
No, sir. No.
So then you've got what type of alcohol is this? Primary, secondary, or tertiary?
Primary.
It's got this carbon atom over here has 2 carbon chains. So that one is secondary. What do secondary alcohols turn into? Huh?
एक ही है कार्बन. अच्छा.
दो sides पे ना. Okay, where did we do redox? We did the entire AS redox before this, I think. So at this point, so we did this, that primary alcohols will turn into aldehydes, and aldehydes will get further oxidized to carboxylic acids. And potassium dichromate 6 or KMNO4, you could use potassium dichromate 6, toluenes or Felling for aldehyde oxidation. Ketones don't get oxidized. The reaction stops at ketones. Now, anyways, so you're seeing the type of reaction. That's obviously a redox reaction. And the functional group change. It changes from a secondary alcohol. What do secondary alcohols turn into? They turn into carboxylic acids. Sorry, ketones. So they turn into ketones, right? And so that's about it. So the next one is the structure of this thing is shown. So that's gingerol. This is something else. What type of reaction is needed to convert? So he's saying what happened here. Like how did this molecule, I mean the OH, turn into an alkene? So how did this is known as dehydration. I mean, you studied this in AS. I mean, I can add dehydration. Dehydration is
a dehydrating agent, which was LiL4.
Okay, so what dehydration does is, it's not LiLH4. I'll just explain. What dehydration does is that it removes the OH from one carbon atom, and from the neighboring carbon atom, it gets rid of the H. And instead you get a double bond in the middle. So there are two reagents. You can either heat it with Al2O3 or SiO2 or pumice and heat it with that. Or what can be done is you can also use, there's another thing that you can use which is concentrated, H2SO4. You can bubble it through concentrated H2SO4. So I think Al2O3 SiO2 should do the job. And the type of reaction needed to convert, that's dehydration.
Sir, catalyst कौन सा?
Al2O3 and SiO2. So the reagents are Al2O3, SiO2, and the conditions are you would have to use heat. And let's just open a marking scheme as well, just to. So it's Al2O3, SiO2 plus heat. I'm just, the temperature should be greater than 450, but I'm just double checking whether they're using that particular temperature. So it's just heat with Al2O3. That's about it. Dehydration, elimination. So that's kind of it. Now, where's the question? This one. I said, what's next? Here's another question which says that it reacts with hot concentrated KMNO4 to form two organic products, QNR. Draw the structures of QNR. So this is about strong oxidation of alkenes. What happens during strong oxidation of alkenes? So this is something that we did in strong oxidation. What happens is that the double bond is going to completely break. Remember your AS organic chemistry. Pretty much a lot of things will come from AS organic. So the double bond is going to completely break. And you will have three scenarios. You're either going to have a carbon with two H's, no carbon chain, turns into carbon dioxide and H2O. If it's got one carbon chain, then that one will turn into carboxylic acid. And if it's got two carbon chains, that one is going to get converted into a ketone. So let's go back. There's strong oxidation happening, and it involves an alkene. So the alkene will split up at this point. And I don't think we didn't do any oxidation of phenol, so nothing, ketones don't get oxidized. So the double bond will break in the middle, right? How many carbon chains is this one attached to? Well, it's only attached to one carbon chain, right? So if it's only attached to one carbon chain, it turns into a carboxylic acid. Okay, so it turns into carboxylic acid. So this one over here will turn into a carboxylic acid. This one also is bonded to, this other one is also bonded to just one carbon chain. So that one will also turn into carboxylic acid. So you're going to get two carboxylic acids. So he was asking you to draw both of them. The middle part is gone now. So the middle part is gone. And the molecule, they're two separate molecules. One of them is this one. And the other one is this entire thing. So the whole redox reaction happened on this double bond. TK, is that clear?
Yes, sir.
Now, so that's Q and R, right? We just drew that. And he's saying, now he's saying that it's, I mean, zingeron is something else. I don't know what that is. Some reaction of zingeron are shown. So it's something that is formed from gingerol, which was, I mean, one of the two structures that were given above. So he's telling us three things, that benzene diazonium chloride at 5 degrees centigrade alkaline conditions, right? So this is the reagent and the conditions, and he's saying that a red precipitate is formed. Now, first one, what is this one? This one is a diazonium salt. So this one is a diazonium salt. We did do diazonium salts. So he's saying that whatever zingeron is, it reacts with the diazonium salts. And there's an observation as well, a red precipitate is formed. So where did we learn about diazonium salts? Diazonium salts we talked about diazonium salts when we talked about dye stuff. We talked about Azo dyes. We talked about that Azo dyes were dyes. They were very stable dyes that were formed when you had a benzene and there was an N double bond N azo group that was between them, and it's a very, very stable dye. And we learned that how to form diazonium ions. Now, the question is about, it's not about making diazonium ions, because the diazonium ion is already there, right? So it's already there. What did you do with the diazonium ion? The diazonium ion was used to make Azo dyes. We learned that you take a phenylamine, you react it with NaNO2 plus HCl, and the temperature's got to be less than 10, because it's a very unstable compound that is formed. If the temperature increases to greater than 10, the N triple bond N plus 1 quickly decomposes and ends up forming a phenol. It ends up forming a phenol and ends up reacting with water, hydrolyzes with water. So, but the point was, what do you use the diazonium ion for? The diazonium ion was a very good electrophile. This is what we learned, that the diazonium ion has positive charge and it will be attracted to the electron cloud in benzene. But the benzene has to be an activated benzene. So it's either got to have an OH group, or it's got to have an NH2 group so that it's activated. The electron density should be higher at positions 2, 4, and 6. So the diazonium ion is going to be attracted to those to that benzene, and it will go and bond with it. And I don't know why this got messed up. Just a second. And it will end up forming an Azo dye. Just hold on one. You can't fix it right now. Anyways, think of this as connected to this benzene. So it will end up forming an Azo group. And this is an Azo dye. This is the colored dye that is formed. So the question is kind of the same. He's adding a diazonium, benzene diazonium chloride, which is a diazonium salt, and you're getting a colored dye. So functional group in zingerone indicated by the observation. So the functional group that it indicates is that there must be an activated benzene, right? Because disonium ions, because disonium ions only react with activated benzenes, and they form colored dye stuff. So there has to be an activated benzene. And I think the reason we can rule out NH2 is, I mean, it's going to be a phenol. The reason we can rule out NH2 is because he said that it was being made from gingerol, which is this thing. That thing never had an N. It had a phenol, it didn't have an N. So that means whatever this other thing, zingerol or whatever is, it definitely has this phenol, because if you add N triple bond N plus 1, the activated benzene is going to react with it, and it will form an Azo dye. So it definitely has this phenol group. Is that clear? What about the next? What about the next one? And the thing is, there's no analysis. You just have to answer this. 2,4-D in pH. What does it identify? 2,4-D in pH.
Ketone and
so it gives a positive result with both ketones and
aldehydes.
But only one of them gets oxidized. So with tolerance reagent, there's no change. So which one is not present?
Aldehydes are not present.
Okay, because aldehydes will give a silver mirror and a black precipitate. So the answer to this one is ketone. So it's just a 2-mark question. So you're going to get, so this would be ketone. So that was not really that difficult. So this is about enema. We haven't done that. So let's continue with more questions related to organic. Okay? Usually there are two big questions on organic in every paper. Okay? So let's continue tomorrow.
Okay, take care.
Okay, take care.